Oh.
That's weird. All right, so we're going to talk about functional groups. This is kind of weird the way it aligns with our book and actually every book. So just keep that in mind. In most textbooks, functional groups are these specific pieces, these bits of a molecule, and we're going to talk about the different types of them. And that's really annoying, I'm sorry. And hopefully we're going to be able to identify them. But the way the books organize it is they do like a chapter for each functional group or each type of functional group. And we're not doing that because we're not going that far in depth. That would be more like an organic chemistry class. So for us, we're just going to do this tiny bit of like 7 chapters. So the way it's listed on the syllabus, it's like 7 or 8 chapters, but it's literally just like the very beginning part of each of those chapters. So we talked already about alkanes and isomers and that kind of thing. What we didn't really talk about is anything about the reactions of those. So what happens is when these molecules react with each other, as we'll see later, the alkane part, the carbon-hydrogen part, that forms the basic structure of most of the molecule, but that doesn't really do the reacting or do anything. It's these other pieces called functional groups that give it the actual reactivity that we're going to be looking at. So we need to know what they're called and what they look like, and then eventually also how they act or how they interact. So functional groups are parts of the molecule that determine its reactivity. And actually, a couple of these we've already seen, but we're going to list them all in so that you have a list of them. And what you need to be able to do is identify and name each of these types of functional groups. And I don't know if it will have time today, but maybe we're going to look for them in some molecules so that we can see if we can find them. All right. Our first functional group that we're going to look at is called the alkyl halides, or an alkyl halide. Alkyl means on an alkane. So we already talked about alkanes, those normal carbon-hydrogen chains. Alkyl halides are things connected to those chains, and the specific things that they are fluorine, chlorine, bromine, and iodine. So you'd have like a molecule like this, which doesn't really do anything reactivity-wise. You can burn it, it combusts, but other than that, it doesn't really do much. But if that molecule happens to have one of those types of atoms attached to it, now it can do a whole lot more stuff. It can do these different types of reactions. And so these can show up in a lot of different forms. You know, you can have multiple ones, depending on what you're doing, what kind of molecule it is. And you'll see these all the time when we look at these different molecules. There's nothing special about the structure or the geometry of them. They just kind of take the place of hydrogen. So as you'll see, when we're counting up a molecular formula, if we look at the second one here, we can count up the carbons, 1, 2, 3, 4, 5, 6. We can count up the hydrogens, which would be 1, 2, 3, 4, 5, 6, 7, 8. And then there'd be 1 hydrogen here and no hydrogens on that 6th carbon because the halogens, the halides, the fluorine and the chlorine, take up those hydrogen spots. So there would be 9 hydrogens, and then the rest of the formula would be like that. Right. So that's the alkyl halides. We've seen some of these before. We've seen molecules that have these things attached before. All right, our second class we've also seen, and that's the alkenes. Alkenes are double bonds. So these are structures like, well, the simplest one is like that. But we see them in bigger structures too. They can be combined with other things. So when we draw alkenes or double bonds in these line structures, usually we draw the regular line structure and then we add a line on one side or the other to show that it's actually a double bond. So this ring structure I drew here, you'll notice the double bond here is between these two carbons. We usually draw it that way instead of like this, but those would both be correct. Both be fine. Just you can see the structure a little bit better on the other one. Or I guess that kind of looks the same. If I tried to make it really even, it'd be like something like that. We usually don't do that. Rather we draw it this way. The geometry of the double bond is a little bit different. I'll try to show you with models if I can together. So you built these models, what did we do, a couple weeks ago? Yeah, it's not going to work. Can somebody build for me? Who wants to build? So take two of the black ones. And so we'll take these carbons and connect them with the blue curved ones, these two of them. Let's put two other bonds. Okay. All right. So thank you very much. So rather than have that three-dimensional tetrahedral geometry that we saw before with the alkanes, we now have this two-dimensional. It's technically still three-dimensional, but it's flat. It's a planar geometry for the double bond. So you can look at it kind of like that. You can see that when we draw this on the screen, it actually is the correct geometry, unlike the tetrahedral one, which had that three-dimensional dash wedge thing that we talked about. So these are flat. The other interesting thing about these double-bonded compounds that is also reflected in these models is they don't rotate. So one of the big issues that we found on the last exam is that it's difficult to sometimes tell if structures are the same or not because single bonds rotate. And so you have to kind of twist things around to see if they're the same as something else. Double bonds don't rotate. You can't twist them. So the consequence of that is that a structure like this, actually let's do it in line structures since that's how we've been doing it. Let's say I have a structure like that with a double bond in the middle and two carbons coming off of it. And then let's say I have this. If those were all single bonds, those two would be the same because they'd be four carbons connected in a row, just twisted. One's twisted, one's like a twisted version of the other. So there's that first one that I drew. and I can't twist it to make the other one. If that were a single bond, I'll just loosen it, I'd be able to twist it, and those two would interconvert. Those two would be the same thing. But because it's a double bond, it's locked in place, and those two are actually different structures. So I can't make the other one this way, unless I actually pull this one apart and stick it on the other side. So let's write that. So that makes these two not the same.
So any alkene that looks different in formula is with a double bond.
If the difference is around the double bond, then that's right, it's not the same. Yeah.
So those are isomers?
So those are actually isomers, yeah. They're a different type of isomers, which we'll get into when we talk about carbohydrates. They're called stereoisomers, but they are, yes, those would be considered isomers. I'll give you the real word for it here, stereoisomers. That'll make more sense in the next chapter, but basically they're isomers that differ by their three-dimensional orientation. So the geometry of it, even though they're still connected in the same way, they are not the same exact structures. All right, alkenes are a source of reactivity. So even a simple molecule like this one, ethene or ethylene, is actually reactive, whereas alkenes like methane and ethane and propane and butane are non-reactive. So that double bond allows them to be more reactive. The other consequence of this that we'll get into in a couple of chapters when we talk about lipids is the geometry of fats. Fatty acids can usually take a couple of forms. So don't worry too much about the rest of this, but you can have fatty acids that look kind of like this. And those are called saturated. And they're these long straight chains because of the single bonds. And then you can have fatty acids that have double bonds in them. And because they don't rotate like that, when the double bonds have this cis geometry, they really change the whole structure of that chain. And actually, fatty acids would have many more carbons than that usually, but we'll just use those because they're easier to draw. So you get this kind of kink in the chain. And this is why unsaturated fats tend to be liquid at room temperature, whereas saturated fats tend to be solid at room temperature. So things like butter and animal fats are saturated fats. Most like vegetable oils and those kinds of things are unsaturated fats. The unsaturated fats can't pack together as tightly because of these kinked chains because of their double bonds. And so they make liquids. It's also why unsaturated fats tend to go bad and go rancid sooner than saturated fats because the double bonds make them more reactive. So they react with stuff and go bad. That's why like olive oil doesn't last very long. It starts to kind of smell bad after a while because those double bonds start reacting with things. Whereas something like shortening or lard will stay good for much longer. So that's alkenes, double bonds. Sound good so far?
What is the last word?
If those aren't the same, they're called stereoisomers. So I should write also here. We'll get into more of those details about the fats. We have a whole chapter about it coming up. All right, our next functional group are called alkynes. Any guesses as to what those are? If alkanes are single bonds and alkenes are double bonds, Yeah, triple bonds. Alkynes are triple bonds. So alkynes are triple bonds between carbon. That's the simplest one. That molecule is acetylene, which is what we formed when we did that pumpkin experiment. We formed acetylene inside the pumpkin, and then we blew it up. I did that again last night with my class. And I don't know if it was just an old pumpkin or I made too much gas in it, but the whole pumpkin just like split apart. So it was pretty spectacular. But at least nobody got hurt until this morning. Triple bonds are linear. So if we put that third bond in, not only does it not rotate, but it actually no longer has any kind of angle or bend to it. Triple bonds have a completely linear geometry, and that's because atoms in general want to be as far away from each other as possible. So the fewer things connected to an atom, the more they can spread out. If there's only 2 things connected to an atom, that means they can spread all the way out and be on opposite sides. If there's 3 things, they have to crowd each other a little more. If there's 4 things, they have to crowd each other a little more. So that's going to be the most spread out linear geometry. So when you see line structures of triple bonds, they stop zigzagging at the triple bond. Whoa, sorry. So you've got something like this, you want to put in a triple bond, it goes straight off, and you can still see where the carbons start and stop, where the 2 carbons are, because the 2 sides of the triple bond are obvious there. They can be inside of a chain also. So this molecule would have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 carbons. So you have the 2 on either side of the triple bond, and then all the rest of them. Since the triple bonds, again, are 3 bonds to carbon, that means those 2 carbons, 5 and 6, on either side of the triple bond, don't have any hydrogens attached to them because they already have their 4 bonds. Our 4th functional group kind of goes with the other ones. It's called aromatic, and it's really a special subset of the alkenes that we just talked about. Aromatic groups are rings, so those closed ring type structures, with alternating double bonds. Those alternating double bonds alternating double and single bonds end up giving these compounds a special stability, which is why we think of them as a separate functional group, even though they're still just single and double bonds. So the most common one that we see in all kinds of structures is this, which is a 6-membered ring, or a 6 carbons are connected around with alternating single and double bonds. And this molecule is known as benzene. It's a very stable molecule. It's totally flat because remember, double bonds are flat. So it allows the ring to be completely flat, very stable, and it shows up, therefore, in a lot of natural products, a lot of biological compounds. Benzene by itself is not great for us. It's a carcinogen. It's a human carcinogen, so it's known to cause cancer in humans. It used to be a really, really common solvent in labs, but we're moving away from it because it's dangerous. But like people of like my parents' generation who went to college in the early 70s, they'd like wash their hands in big tubs of benzene because it was a good solvent and it would wash all the stuff off before they left lab. We don't do that anymore. But these types of things, because they're so stable, they're often formed as combustion byproducts. So if you burn something, but there's not quite enough oxygen to burn it completely, you're going to form aromatic byproducts. So things like benzene. And then these rings can hook together in various ways. This is called biphenyl. You can hook them together kind of honeycomb style too.
So it always maintains that shape.
Not quite. Whoops. You can also have smaller and larger rings, but they usually have to then have other types of atoms in them. So like this is a common one, which is a 5-membered version of that. There's also a nitrogen version. There's a nitrogen version that has 6 things in it too, which is called pyridine. They all kind of have these special names. Anyway, you can have kind of bigger ones, but they're usually based on this 6-membered ring benzene structure. These types of structures, especially these and bigger ones like it, are one of the reasons why smoking is bad for you. Because when you burn stuff in a relatively low oxygen environment, you produce a lot of different types of carcinogens, including these. And that's why it's like inherently kind of bad for you. It doesn't really matter what kind of additives or whatever are in the cigarette. Anytime you burn something, you're getting these kinds of things. And so it's not just smoking, it's things like grilling and smoking meats and that kind of stuff also are usually producing these types of compounds. It's just in those cases, you're not usually taking all the smoke into your body on purpose. It's just, you're just getting a little bit of it. So those are aromatic compounds. We're going to see this a lot as we look at different atoms or different molecules. You'll see it popping up all the time. All right, where are we? Okay. Our next functional group are the alcohols. Alcohols are molecules that are, parts of the molecule that are OH. And we learned to look for those when we talked about intermolecular forces and hydrogen bonding. But this alcohol functionality is really important in most biological molecules. Sugars, when we talk about carbohydrates in the next chapter, we're going to be drawing lots and lots of those. They can be at the end of a chain. They can be at the middle. They can be attached to different types of rings. A couple common alcohols that you may have seen. If you have 2 carbons with an OH, that's ethanol. Ethanol is the waste product that you get when yeast metabolize sugar, and that's what like alcoholic drinks come from. That's called ethanol. We just call that alcohol sometimes, like colloquially, but alcohol is actually a functional group. There are lots of different types of alcohols. This is the one that we drink, but interestingly, a couple other ones are not so great. So if we just have 1 carbon instead of 2, we have methanol. Methanol is very poisonous, sometimes used as a specialty like rocket fuels and that kind of stuff. You definitely can't drink that. And in fact, the ethanol that we use in lab most of the time is called denatured ethanol, which is ethanol that has poisonous stuff added to it, so you can't drink it anymore. So that way, it makes it a lot easier to buy and sell and ship. You don't have to worry about all the taxes and controls on drinkable alcohol. So don't ever drink lab alcohol. I mean, don't drink stuff in the lab anyway, but if you're like, oh, that's the same as in my beer, then you don't do that. And then another common alcohol that we see is isopropanol or isopropyl alcohol, which is rubbing alcohol. So again, similar, 3 carbons with the OH coming out of the center. Alcohols are named in a couple different ways. The names I wrote here are kind of like the official systematic names, but the older names are to use that YL type naming, and then just say alcohol. So ethanol is sometimes called ethyl alcohol. Methanol is sometimes called methyl alcohol, and isopropanol is sometimes called isopropyl alcohol. Those are the same things. So we'll see lots of alcohol functional groups too. Okay, similar to the alcohol, but less common is the thiol, which is SH. One of the nice things about looking at these two is that it really shows some of what we can do with the periodic table. We know that atoms that are on top of each other in the periodic table in the same groups, same families, those are sometimes called, have the same number of valence electrons. That also means they're going to have similar properties and similar behaviors. So a lot of the compounds that oxygen can do, and a lot of the ways that oxygen binds and makes stuff, sulfur also does, because it's right underneath oxygen, still has 6 valence electrons, does some of the same types of things. Where it differs, of course, it's a different atom. But the types of structures look the same. It's going to react a little bit differently because it's sulfur, and a big difference is that the way that it interacts with our bodies. Our bodies know that there's a huge difference between oxygen and sulfur, so even if the compounds are sort of the same, they change in a big way when they get into all our receptors. And one of the ways for that is smell. Thiols smell terrible. They all pretty much smell bad, and they're responsible for a lot of the bad smells in our world. Specifically the kind of like, I don't know how to describe it except like farty smells are usually thiols. So things that kind of smell like farts and poop and like that specific type of really bad smell is probably thiols. Also that, whenever you hear of like a sulfury smell or something smells sulfury, again, those are thiols. Sulfur itself, the pure element, doesn't smell. It's that it produces hydrogen sulfide and other types of thiols, and that's what you're smelling when you smell sulfur. So like the molecules that are added to natural gas to make it smell are thiols, so that you can smell it at low concentrations so that it's safer. All right, and then we've got ethers. So with ethers, we're going to use this notation that we'll end up using more later. Looks like this. So R. There is no element R. It's kind of like a wild card. It's just saying something with carbon in it. Some kind of carbon-based something. And if you want to talk about different carbon-based somethings, you use the little prime or apostrophe. So this says you've got some carbon stuff on one side, you've got some carbon stuff on the other side of the O, but it doesn't necessarily have to be the same stuff. So molecules like this kind of looks like a bat, very Halloween-y, but it's called diethyl ether. So there's 2 carbons on either side of the oxygen on that molecule. And then you can have ethers inside rings like this. You could have different amounts of carbon on either side. This molecule is called dioxane, which is was a really popular solvent. It's really also bad. It's also a carcinogen. And for a long time, it was just dumped into the environment by manufacturing companies making various things. So there is a lot of polluted water that has dioxane in it, and that's a big problem right now with specifically polluted waterways. This molecule, diethyl ether, is a really common organic solvent. It has a very low boiling point. Its boiling point is about 35, so just a bit above room temperature. And As long as you don't need to heat it up too much, that makes it a really nice solvent because it evaporates really quickly and easily and then leaves your stuff behind. It is also a little bit dangerous because those vapors are flammable. So you have to be careful to work in the hood with that sort of thing. It was one of the first anesthetics with chloroform where you could have something that somebody could inhale and then not have to have surgery awake, which is good. It's always good to not have surgery awake. The problem with it is it kind of messes with your body, makes you throw up, can make you really sick, can kill you pretty easily if you accidentally inhale a little too much of it. So it is not ideal, and we don't use it anymore for an anesthetic. But if it's between that and being awake while somebody does surgery on you, probably going to go with the ether. Just personal choice, I guess. People do it as a drug too. I don't know if you've ever heard of that. They just call it ether. You can inhale it. And again, there's plenty of other great drugs out there. You probably don't need to worry about this one, which is pretty dangerous and not all that pleasant from what I've heard. Is anybody's favorite drug? Sorry if I offended you. What's your favorite? Is it?
It's when you're in Living of Las Vegas.
Is it?
Yeah.
I didn't see that one.
What's his name? The journalist.
Yeah, Hunter Thompson.
Yes, yes.
Yeah.
It's very good.
All right, so in lab, we're all going to get some ether, and we're not going to do that. Yeah.
Living of Las Vegas.
It's like a book and a movie, right?
Movie.
All right, so our last functional group of this type, where it's just like stuff connected to carbon stuff, is the amine, which is nitrogen with two other things connected. It can be hydrogens, but they also can be other stuff. Amines are also really important in biological systems because they are a major component of amino acids. So every amino acid has this type of structure or slight variations on that, where you have this thing on the left, which we'll talk about in a minute, called the carboxylic acid. You have the amine on the right, and then you have some other thing coming off of it. And depending on what that other thing is, that R, that's what gives you all the different amino acids. You look up a chart of however many, do we know how many there are? 20 some, do you think?
20.
What? 20 amino acids. So they all just differ by what is in that R position. And we'll look at some of them when we get into the proteins chapter and talk about how they're together. But that's where that word amino comes from, is that amine functional group, that NH2 on there. You can also have smaller amines like this. You can have ones where the nitrogen has just a couple things attached to it, or I'm sorry, just two carbons and one hydrogen. You can have things where the nitrogen has all carbons attached to it and no hydrogen at all. Those are all considered amines as long as the nitrogen only has single bonds. Amines are also responsible for a lot of bad smells. So if the, it's just a catalog of bad smells really. The sulfur ones were all the like poopy farty smells. The amines are the more decomposing death smells. I don't know if that is familiar, you know, if you've ever smelled things rotting, that's amine type smells usually, because the things that are rotting are usually made out of tissue, which is made out of proteins primarily. And so when those start being broken down by the bacterial activity, they're producing amines from there, and that's some of those smells that you're getting in that decay. So like that dead fish smell, that's an amine. The like roadkill smell, that's an amine too, or a couple of them together. Okay, our next several functional groups here are all related in that they're called carbonyl functional groups. So let's talk about what that means. A carbonyl is a group on a molecule that has a C double bond to an oxygen. And then since C needs 4 bonds, there's going to be some other stuff coming off of that C. But that thing by itself is called a carbonyl. The functional groups all depend on what is connected on either side of that carbonyl. So if we have something here and then something here, depending on what's in those positions, the functional groups have different names and therefore different reactivities and different ways they behave and different types of compounds and all of that. So this is maybe the hardest part to keep straight of the functional groups is this next list, which are all fairly similar but differ by what's on either side of the carbonyl. Let's see, what number were we on here? 8. We'll go with 9 is aldehyde. Aldehydes are molecules that have carbonyl, a hydrogen on one side, and then some carbon stuff on the other side. So because there's a hydrogen on one side, these will always be at the end of a chain or at the end of something or coming off of something because they can't be in the middle because they have to have hydrogen on one side. So you'll see things like this. We can have a benzene ring with an aldehyde coming off of it, like that. The simplest aldehyde actually doesn't have any more carbons. That's formaldehyde. And then sometimes when you see it in larger compounds, especially when we talk about sugars, aldehydes are really important in many of the carbohydrates. They're sometimes written as CHO as an abbreviation for that C double bond O and then the hydrogen. The reason it's done that way is because COH would be ambiguous because it could be OH like an alcohol. So if you write CHO, we know that the O isn't connected to the H because H only gets 1 bond, so we can know that that's supposed to be an aldehyde. And the key to finding or to identifying the aldehyde is looking for that hydrogen that's connected to the carbonyl. Question?
For the ether and the aldehyde, what is mean by like some carbon stuff?
Kind of like what we drew here. So R could be like this, could be this, could be it could be just like some other part of the structure that could be whatever. Let's see. What is it? It is this molecule. It's used as a preservative. So you put like samples in it. Yeah, you put your dead animals in it or your tissue samples or whatever, and then they won't decompose. I don't know if it's used. I don't think it's used in embalming. I don't think it's used much anymore at all. You know, I don't know. They don't use it in embalming, no. I think it's more like we got the jar with the like frog in it or whatever. That's probably got some formaldehyde in it, especially if it's old. Now they use some different compounds that are a little bit less stinky and less, I think this is a carcinogen too, so you got to be careful with it. I know like in biology department, they use some dilute solutions of formaldehyde for some of the preserving down there. Aldehydes are also smelly, but sometimes kind of like formaldehyde. Some people like the smell, some people don't. But a lot of aldehydes smell really nice. Things like vanillin is an aldehyde. Cinnamon is an aldehyde. Some of those other types of spice, perfumey kinds of smells and flavors are aldehydes. All right, so related to aldehydes, and sometimes hard to tell apart, are the ketones. Ketones have the same left half, let's say, as an aldehyde, but the right half is more carbon rather than hydrogen. So that's how you tell an aldehyde from a ketone. The ketone has carbon on both sides, and the aldehyde has hydrogen on one side. So some ketones. So ketones can actually be inside of rings, can be in the middles of long chains, because they have carbon on both sides. A simple ketone like this that has 3 carbons, the simplest ketone, is acetone, which is a good solvent. I think we've used it in lab. It's also used in things like nail polish remover. It's a good solvent for both polar and nonpolar compounds. It's polar because of the CO, but it's also a little bit nonpolar because of the carbon and hydrogen on the bottom. Yes, ketones are a big part of your body. Yeah, Andrew.
What's the difference between the acetone and
They do. So formaldehyde, the formula is CH2O. So there's only 1 carbon in the middle there, and then H's, and then an O. Acetone, the formula is, or the molecular formula is C3H6O, because these are actually carbons instead of hydrogens. So they look similar, but they would have carbons on either side instead of hydrogens.
What are the hydrogens in formaldehyde?
They're shown. They're right.
Oh.
These two, here and here.
Yeah, that's stupid.
Yeah, and the carbon in the middle doesn't have any more hydrogen because it's got 4 bonds already. But yeah, ketones are all in your body. Anything in your body that ends in -one is probably a ketone. So things like hormones, which also generally have the suffix -one, are types of ketones. Ketones are also produced as a byproduct of metabolism when you don't have enough sugar. Yes, when you don't have enough sugar, your body produces ketones. And so that's why there's things like the keto diet that you hear about, things like that, that you're, you can, and there's also what is it? Yeah, but what is it if you're diabetic there and you have too much sugar, I believe, or not enough sugar? I don't remember. Somebody know? We should look this up. Yeah, one of those conditions, you end up like, you can smell like weird chemicals on somebody's breath, and that's the ketones that's coming out from the metabolism. I think it's because they have too much sugar, but that could be backwards. Sorry.
Is it ketoacidosis? Yes.
Maybe. Is that right?
Yes.
Okay, thank you. So is that from too much sugar or not enough sugar? Too much insulin. Okay. So the sugar drop. That would make sense because then you produce ketones from. So the sugars get metabolized into ketones instead of the other stuff they're supposed to get metabolized into, energy, whatever. All right, we need to like co-teach this with a biology person so that we can fill in all these blanks. And I'm like, I don't really know. Where are we? Okay. So, okay, so we got aldehydes and ketones, and you can tell them apart by whether or not they have that hydrogen connected. Next, we have carboxylic acids. These are, as the name says, acids. So these are when we talk about organic molecules that produce hydrogen or hydronium in solution. These are the acids. Carboxylic acids are a carbonyl group with, again, some stuff connected to it. And then on the other side, it has an OH. So that H from the OH is the source of hydrogen on the carboxylic acid. So we've used some of these before, like just on Tuesday in lab, we used this one, which is acetic acid. You can see the carboxylic acid part right here. Carbon, double bond to oxygen, and then the OH. And then there's another CH3 over here. So that's why we sometimes see acetic acid's formula written in a couple different ways. Sometimes it's written CH3CO2H. Sometimes it's written with its full formula like C2H3O2H. or sometimes we put the H first because it's an acid. Either way. Carboxylic acids can sometimes be hard to find or hard to identify if we don't see the whole structure because they're often abbreviated as either COOH or CO2H. And if you don't know that, that can be confusing because you would think of COOH as being like C, then O, connected to O, connected to H, but that's not what it is. It's C with double bond to oxygen and then an OH coming off of that carbon. So when you look, when we do our activity to look for some of these functional groups, which I don't know if we'll get to today or not, yeah, maybe we will. We're looking for those kinds of things as well to find carboxylic acids. Carboxylic acid then is the other half of, let's go back up here, the amino acid. So you've got the amine on one side, the acid on the other side, and that makes your amino acid. Most of these acids are named with something ic and then acid, so acetic acid, just like our other acids that we've looked at. You can have it connected to benzene. That's called benzoic acid. I think that's used in some like face cleaning products, that kind of stuff. Acids can also be a little stinky. They are, this is called butyric acid, like butane. It's got 4 carbons. They are the products of the decomposition of fats, which we're going to do in lab next week when we make soap. So any of those kind of like rancid fat smells, rancid buttery kind of gross smells are probably some of these. So those of you who are kind of holding your nose at some of the milk smells last week, some of those might have been carboxylic acids that were being formed. Things like, I don't know how to describe it. I should just get some and we can smell them, but they're so bad. People like throw up. But if you can think of like a bad buttery smell, like something smelling kind of cheesy or buttery that you don't want to smell cheesy or buttery, that's this kind of stuff. I don't know if that's helpful or at all. But like if you smelled a person that smelled kind of like cheese, like that's probably these types of things coming off. Your question, Ian?
How much of this are we supposed to like be able to identify?
So you need to be able to identify all the functional groups. You don't need to remember the names of the compounds or anything.
Okay.
Yeah, that's what I was gonna ask, like on the test, is it gonna give you a structure and say which functional group is this?
Mm-hmm.
Sweet.
That kind of
So
stuff.
we're not gonna need to have to like know how to name it.
We just know what the name of the functional group is, but you don't need to know how to name the compound, like the whole compound, right? Yeah.
Do we need to know how to write them and call them out?
Yes. So if I said, so what I might ask you is like, in one way, I might give you some big complicated molecule and say, circle and identify all the different functional groups on this molecule. Because molecules can have any combination of any of these things together. So you could find 10 of them or whatever. The other thing I'd ask is draw a molecule that has a carboxylic acid and amine functionality. And you can draw a molecule and have a carboxylic acid and it.
Like the multiple choice section, is there gonna be like specific answers like little details?
No, none of the details about smells or anything like that. Just can you identify these functional groups? And we'll do a quiz on this next Thursday, so a week from today. And so Tuesday we'll practice a little bit more. Let's finish up talking about the rest of these couple, and then I'll show you an example of how we can find some of these. Okay, where am I at here? Carboxylic acid. So then we've got, related to a carboxylic acid is an ester. An ester has that same start, but now instead of an OH, it has an O with some other carbon stuff on it. So again, sometimes that's abbreviated like CO2R or COOR. Something like that would be an ester. So kind of like a carboxylic acid, but instead of OH, it's O with some other carbon stuff. Esters can be inside rings. We're going to see some esters like that when we talk about the sugar stuff. These are sometimes called lactones. But again, it's got the oxygen and then other stuff coming off the oxygen that is not carbon, or that is not hydrogen. It's generally carbon. Unlike some of the other stuff we've looked at, esters are good smelling. They're also smelling, but most fruit smells come from esters. So if you think about the smell of like raspberries or bananas or those kinds of things, they're generally, with the exception of citrus, which is a little different, they're usually esters. So a lot of perfumes and lotions and that kind of stuff have esters in them for the fragrance. And our last one is amide, or some people call it amide. And it is similar to the ester and the acid, but with nitrogen instead of oxygen. So you've got a carbonyl, carbon double bond to oxygen. That's then connected to a nitrogen, and then that nitrogen can have whatever connected to it, hydrogens or not. So in a molecule, that might look like something like that, or there could be carbon stuff connected to the nitrogen also. But the nitrogen being next to the carbon that's double bound to the oxygen is what makes the amide. And this is how proteins are put together. So if we take, let's out of the way a little bit. If we take a couple amino acids, like let's say this is glycine. And this is alanine. The way those two would come together, and we'll talk about this more in the protein chapter, is the OH and one of the hydrogens here would come together to form water. And the result of that would be that these get hooked together in an amide bond. And now you have a peptide, which is more than one amino acid hooked together. So if you look at that middle linkage here, where they got connected together makes an amide. And so this would be a glycine alanine peptide, which would be written like that. We'll look more about those when we get into the protein chapter. But that bond sometimes is called a peptide bond instead of an amide bond. Because when it's used in the protein context. All right, so those are the different functional groups. So take a look at your list, and I'm going to pull up some random big molecules. And with our last few minutes, we'll see if we can identify some of these different ones. One way to practice this, if you want, you can go to the ACS publications, which our library has a subscription to. These are all big chemistry papers. And you can, if you go to the library site, you can access them on your own computer or off campus. And you would go to something that says something about organic chemistry, like Journal of Organic Chemistry. And let's just pull up some random big synthesis here. I can't quite because you have to go through the library's site to get there. So if you just go to the library in the databases and go to the ACS publications, that's what this is. But you can look at any kind of organic type papers. So let's grab one of these. So this is how somebody would report the chemistry that they've done. And one thing that they would do is they would report all these different molecules that they made and how they made them. And we can look at those and find some of these functional groups. So let's take a look here. So these are a little bit, they have R's, you can see, because they're talking about a whole bunch of different things at the same time. Let's see if we can find one where the atoms or where the molecules are more clearly. Here's some. So we can look at some of the things that they've done. These are reactions they've reported that work in various ways. So let's just look at a couple here. Okay, who can find some functional groups? Raise your hand if you think you see one. Yeah.
Is that bottom one of the acetone?
That is acetone. So what kind of a functional group is that? That's a ketone. Yep. So there's a ketone right there. What else can you find?
Aromatic.
Yep. There's aromatic rings here, here, there. Yep. What else do you see?
Would ester be the 2A?
Close. There are ethers. So one thing that you'll find here, ET means ethyl, which is 2 carbons, and ME means methyl. So actually this is an ether here, because that would be, that ME means CH3, and so that would be CH3O and then connected to the rest of this stuff. So that's an ether. The blue one, so they say ET, which means ethyl, which is CH2CH3. You don't have to know that. What do those 2 O's in a row mean?
Ester?
Yeah, that it's an ester. So the 2 O's in a row actually mean that one of the O's is double bonded to the carbon and the other one is in between. So that is an ester. Anyways, see something else? We saw aromatic, we saw ester, we saw ether, we saw ketone.
There's an NH2.
There's an H2, so what is that?
Well, that
Is it with the D or with the N?
is it an E or is it an I?
Well, you tell me. How do you tell the difference?
Well, I don't know. That's what confused me the last one. I
So
think it's an amine.
What do you think?
I just have no other question.
Yeah, go ahead. Go back then.
There's 2 O's in a row. Can it also be a
Yes, it depends on what's on the other side of the 2 in the row. So if it's an H, it's a carboxylic acid. If it's a carbon thing, it's an ester. Okay?
Yeah.
So back to this question of amine versus amine. It depends on what the nitrogen is next to. So if nitrogen is next to a carbon that's double bond to oxygen, that makes it the amide with a D. That's why I pronounce it differently, so there's not confusion there. Amide with a D, amine with an M. These are not next to carbons with double bond to oxygen, so that makes them amines. An N, amine.
Is considered organic?
Yeah, this is kind of the basis of organic chemistry. Yeah. This stuff is definitely organic chemistry. So organic chemistry is more like, once you know the functional groups, how can you predict that putting those things together with those reagents is going to make that? That's organic. And for these people, I mean, this is like research chemistry. So this is saying like, let's try this and see what happens, and then report that we got this to work in whatever particular way. So that's what this is all about. Yeah.
One more time, can you explain the difference between carboxylic and the ester?
Yeah, let's see if we can find one here. Oh, well, we'll get to that. So just as an example, because I didn't see this before. So here's an example of the difference between an amine and an amide. in this structure here, which is some sort of a important pharmaceutical molecule, I believe, you see here this nitrogen is part of an amide because it's next to the carbon double bond oxygen. All the other amines in this structure are just amines. This one's a little weird because it has this other thing, but the other ones are amines. You see that, the difference? So this one right here is the amide because it's next to the carbon double bond to oxygen. All right, so back to acids versus esters. I don't know if we're going to find anything like that in this particular paper. Yeah, I don't see it. So let's go back to the notes here. The difference between the carboxylic acid and the ester is what's connected to the oxygen. Maybe we should highlight that. So in a carboxylic acid, it's an H. In an ester, it's carbon. Yes, the single bonded oxygen. Is that?
So it's just carbon versus nitrogen.
Right. So what is that second oxygen bonded to? Is it bonded to carbon or is it bonded to hydrogen? That's what tells you those two.
We go back to the
Oh, like stop doing this and go back to math stuff? No, sorry. You like the math stuff better? It'll all be fun when we get into carbohydrates the next chapter and you can like have all these weird structures that you have to be able to flip around in your head and figure out. What?
define.
I don't know. What do you like to do? It's fun. All right, so to work on this stuff, this is the one area of chemistry that is more like anatomy or some of the other classes that you just have to kind of memorize these things. So it could be helpful to make flashcards or make notes or something where you have these names and then the types of thing that they are, and then practice drawing some molecules that have those things in them. And then you can always send me pictures of them if you're looking through the stuff and say, hey, does this have I think this has a carboxylic acid in it, but I'm not sure. What do you think? I can respond to.
Bring back some, let's see the.
Yeah, what were we going to say?
Can we go over each of them and just like, point out the main thing and looking for each one?
Yeah. So let's go through them and point out the main thing that distinguishes them. I tried to write it, but let's point it out to be real clear. So the alkyl halides you're looking for those atoms, those halogen atoms. The alkenes, you're looking for a double bond. Just a double bond.
So any double bond?
Well, okay, between carbons. Between carbons. Double bond between carbons. Alkynes is triple bond between carbons. Aromatic is these rings with alternating double bonds, usually benzene. Alcohol is OH, looking for OH. Thiol, SH. Ether, it's an oxygen in between two carbons, but not with double bonds around. Does that make something, like a carbon double bond oxygen, sorry, not with carbonyls around. Carbon double bond oxygen next to that thing makes it an ester instead of an ether.
Can you tell us how to text you in our mind? No, I don't know how to do that.
Yeah. Does anybody else not know how to do that? Okay. Do you have the app? Okay, so get the app, and then I think it's just, the code is on Blackboard, I think, right? Of like what you need to put in there. Yeah. Although they just told us that we shouldn't do it, but it's okay, we'll still do it for this semester. Use apps like that to communicate with students. Yeah. Apparently, because the app isn't secured, so that the education privacy laws, they don't necessarily conform. So like, I don't think it's a big deal if we're just talking about this kind of thing, but I can't tell you like what your exam score is on it. That kind of thing. I think that's okay. I don't know. We'll use it for the rest of the semester, and then we'll see. So all right. So where were we in the list? So ethers, you look for the oxygen in between two carbons, but not with the carbon double bond oxygen bias. Amines, you're looking same kind of thing. You're looking for the NH2 or the N whatever. You're looking for nitrogen, but not with the carbon double bond oxygen next to it, because that makes it an amide instead. And then there's all these carbonyl-based ones. So the aldehyde is the carbonyl with the H on one side. The ketone's the carbonyl with carbon on both sides. Yeah. The carboxylic acid is the one with OH on one side. The ester is the one with O and carbon on one side. And the amide is the one with nitrogen on one side of the carbonyl. So that's how I group them with the carbonyl one separately, because those have a little bit different way of defining them. Those are the things that you're looking for. Molecules can have multiple functional groups. If you're looking through various random things like structures of medicines, and there's other functional groups that we haven't gone over, so this is not exhaustive. So there are other kinds of things that we didn't talk about, but this is a good start of the most common ones.
What did you say ester was the main thing?
You got the carbonyl, and then the oxygen on one side of the carbonyl. Connected to carbon stuff and not hydrogen. So on Tuesday, we're going to do an activity where you go search for molecules and find all the functional groups, and it'll give us a little bit more practice. You can work on that over the weekend as well. And we'll have the quiz on Thursday. If those of you who weren't here on Tuesday, if you want to stick around and get your exams back, I have them in my office. And if you want help with remind or something, yeah, we can
Do you
do
know
that.
the color off the top of your head?
I think I'm in Blackboard here, so I can tell you.
Okay.